Let's focus now on local deployment options. And the question here is, which one should we choose? An atom, a molecule, or a private atom cloud? Let's take a look at each. The majority of customers who choose to have a local deployment choose a local atom, and that's what we'll cover first. A local atom is a single tenant, meaning it belongs to a single account. It's a single tenant, single node, AtomSphere runtime engine. If you need to connect to applications and data locations within your local network, you will need to install an atom on a machine within that network. The atom needs to be able to connect to the other on-premise applications or servers. You don't need a local atom on each application or server that you are trying to integrate, nor does the atom need to be installed on the same machine as the application. There are some minimum hardware requirements, but they are pretty basic. Here is a simple illustration of the atom behind the firewall, connecting to local applications and to cloud applications as well. So you will choose an Atom runtime if you want access to local or on-site endpoints, perhaps like a database, file shares, or on-premise APIs, or cloud-based platforms and APIs as well. You will choose an Atom runtime also if you're able to procure and manage your own local server environments. Perhaps your organization restricts locating data in shared environments, so the local Atom meets this requirement since no data is passed to the platform. You would choose an atom if your performance or throughput requirements are not excessive. Now that term, of course, everyone asks, what does excessive mean? Well, under a normal setup, an atom can handle processing of around 100,000 documents per month. That, of course, also depends on the size of the documents, but it's a general rule of thumb. Supersize atoms refers to an atom with more system resources allocated to it. It's not a separate entity from a normal atom. By default, the machine allocates 1 gigabyte of RAM for the atom heap. If your machine has extra resources available, you can allocate more heap to the JVM to increase throughput. You can upgrade the machine's CPU also so that it has more resources to have more simultaneous executions. So some of the pros of the local atom are that it has access to local resources, that it can also access cloud-based systems, and you have more control over the resources, configuration, and authorization modes. Some of the drawbacks are that you must procure, set up, and manage your own servers. This is not a suitable setup for large volumes or high performance, and it does not ensure high availability. The molecule is the second most often used local runtime. A molecule is also a single tenant, but it is a multi-node AtomSphere runtime engine. You cannot convert or group multiple atoms into a molecule. It is a separate entity with a separate installation file. Molecules consist of multiple nodes that are installed on multiple on-premise machines. The nodes on the machines are grouped together to form a molecule. Molecule is a single logical runtime entity. It counts as one runtime for licensing. Clustering provides higher capacity, load balancing, failover, and redundancy. The hardware requirements are similar to the atom for each node of a molecule. It's important to note each machine needs to be running the same OS, and you will need a single shared file system. This is an illustration of a molecule. The gray rectangle is the molecule. It is made up of 3 clustered nodes and a single shared storage. The nodes can be on separate hardware boxes, or they could just be virtual machines on the same box. For full high availability, you would want them on different boxes so that if one should ever go down, the others are likely to still be up. So what would make you choose a molecule over an atom? Well, that would be if you need high availability and if you process a high volume of data. If that's the case, then a molecule might be right for you. Molecules provide high availability by having multiple runtime instances running. So clearly you have more processing power to do more at the same time. The setup also provides great failover capabilities. If one node server crashes, you still have other nodes running to do the work. For true high availability, you would need to ensure that your other components are highly available as well. So that would include your load balancers, shared storage controllers, disk and network settings as well. Next, pertaining to high volume, a node allows you to have simultaneous executions. Overall throughput can be higher than a single atom because execution load is divided across multiple machines, so you can do more at once. Further, the processing of large data sets can be spread across multiple nodes. This would require conscious effort in the process design to make use of the flow control shape, but it allows you to leverage this benefit of using a molecule. Let's clear up a few misconceptions that are common when people compare atoms and molecules. The first misconception is that molecules are faster than atoms. You think that more power is more speed, right? Well, while overall throughput can be greater, you have more nodes working at the same time, molecules are not inherently faster at an individual execution on a single node level. So if you run a process on an atom and the same one on a molecule, they would execute at the same speed. If you run a dozen processes on each, the molecule would perform better because it can divide that workload between multiple nodes. But each individual execution would not be any faster than if you ran it on an atom. Another misconception is that molecules load balance real-time executions. You've heard that molecules can do load balancing, so that means my real-time integration is balanced. But that's not true. Molecules automatically load balance scheduled executions. However, an external load balancer is required for inbound web services requests. Another misconception is that molecules provide mid-execution failover. You hear that these provide failover, so if a process dies, it's picked up on another node. No, that's not the kind of failover we're talking about here. A process failure does not automatically continue or resume on another node. If a process fails, unless the exception is handled, that process will stop and generate an error. Molecules provide load balancing in the sense that processes can continue to execute even if one or more of those nodes is not operational. A further misconception is that molecules automatically process large data sets in parallel. Some people hear multiple nodes and assume that every execution can make use of all the nodes. Now, while it is possible to split large data sets and even process in parallel across multiple threads within a single node, or even across multiple nodes or a combination of both, that does not happen automatically. Processing data in parallel is a conscious design decision using the flow control shape within your process. A final misconception is that molecules experience downtime during version upgrades. This is not true and highlights a nice feature. Molecules can do a rolling restart of each node to apply monthly atmosphere updates. This means there is no overall downtime for the molecule. These settings can be configured in the platform. So let's examine a few of the pros and cons of a molecule. The pros, we said that it can access local resources. It also has high availability architecture, supports failover, and scheduled execution load balance. It's very suitable for large volumes and high performance. You have greater configuration, tuning, and setup option, and no additional data volume fees. Some of the drawbacks are that you must set up, manage your server on your own. There is a higher level of setup and configuration and management required. There's also the possibility for an additional cost for molecules if not included in the purchased edition. Enterprise or Enterprise Plus editions get 2 free molecules. Everything else will require an additional purchase. A group of atoms is not really a runtime, just a configuration of atoms. And we'll have some slides to compare a molecule to the group of atoms so that you can understand the differences. Let's first talk about what a group of atoms is. It's a number of individual atoms used for load balancing incoming web service requests. Each atom is installed and configured separately, and each atom is its own logical runtime entity. They are not clustered together. So these loose groupings occur in the production environment and in the external load balancer. So why would anyone want to use this setup? Well, perhaps you have a group of atoms that allow you to fine-tune the runtime configuration and server specs according to your specific use case. So for example, you can configure in your external load balancer some executions to go to an atom with high processor and low memory disk for real time because of concurrency, while some other web service requests may need lower processor but higher memory and disk allowances for larger batch datasets. You cannot have this level of configuration with a molecule. So a group of atoms can be used for better optimization of critical processing, but requires more configuration, more servers, licenses, and resources. This illustration gives you a sense of what a group of atoms could look like. You are getting inbound web service requests from everywhere and all different types of requests. You have the external load balancer in the perimeter network, or your DMZ, and that load balancer routes specific processes to finely tuned atom runtimes. The big difference between molecule and a group of atoms is that a group of atoms are separate logical runtimes versus a single logical runtime with a molecule. So that means if you're considering backup or disaster recovery, a molecule is a single directory to back up. Atoms must be individually handled. So just keep in mind that whatever setup and work and maintenance and monitoring you do in a molecule would be doubled in our previous example where a two-atom group was working. There are implications for horizontal scaling as well. Adding a molecule node does not require additional platform configuration. Adding an atom does. You have to attach the atom, re-enter passwords and manage extensions, and perhaps set up and configure the web services server settings as well. Horizontal scaling requires some thought too. For a molecule, you must consider that at some point adding more nodes within a single molecule doesn't make sense because of contention to shared storage on that machine. For the group of atoms, you must consider that each new atom consumes licenses, even if they're all in the same environment, whereas adding a node to a molecule does not consume more licenses. Here are a few other considerations. Regarding web services, both the molecule and group of atoms would require an external load balancer to distribute requests. For web service authentication, if you use HTTP basic auth, the group of atoms cannot share tokens across the servers. They are unique individual runtimes. So, however, client cert or external auth schemes can be configured consistently across the group. When considering stateful integrations like ETL, batch, or scheduled tasks, the molecule can ensure that processes only run once at a given time across a cluster. The group of atoms cannot ensure that. You cannot share atom queues across separate logical atoms in a group of atoms. As far as runtime monitoring is concerned, these are basically the same. You would monitor each node or atom JVM separately. Let's take a look at a private atom cloud. This is a multi-tenant, multi-molecule AtomSphere runtime engine. Unlike atoms and molecules, a private atom cloud can be used by multiple accounts. An atom cloud consists of one or more cloud molecules installed on multiple machines. So the cloud molecules on the machines are grouped together to form an atom cloud. So who would use this? Well, this would be for someone who is a Boomi partner who wishes to offer a seamless hosting and integration service to multiple customers. Or perhaps you are a large enterprise who wants to offer an integration utility to your multiple subsidiaries and business units. This is the most complex and resource-heavy runtime that we offer, and this is certainly not for everyone. This is an illustration of a private atom cloud, and you can see here the multi-molecule architecture. Now, very likely you would have more than two molecules, and very likely there would be more than two nodes in each molecule, but we simply don't have the space on the screen here to show how large this can get. But this all depends on the specific requirements of the private atom cloud. So in the private atom cloud, you gain a remarkable level of processing power. Forked execution is enabled by default, which allows each integration process to execute in a separate Java virtual machine and which is not enabled in a molecule by default. You also gain another layer of optimization and load balancing. So the molecule can do load balancing on its own, and with a private atom cloud, the Dell Boomi platform automatically assigns each account to a particular cloud molecule based on the number of accounts, so that processing spreads across the available cloud molecules. It also costs more. Clouds must be enabled on your account to create a private Atom cloud, which means that not everyone has this setup available to them. So let's review some of the pros and cons. Some of the pros are that a multi-tenant architecture supports multiple organizations seamlessly, and the high availability architecture supports failover and load balance. It also has high security as each process has its own JVM. There are no additional data volume fees to consider. Some cons to consider are that you must procure, set up, and manage that server set. There is certainly a higher level of setup, configuration, and management required. And there's the possible additional cost of an Atom cloud for each molecule. At this point, you probably have a good idea of what runtime you need, but let me throw a curveball and tell you that you can also have a hybrid approach. A hybrid approach to architecture would be to utilize both the Boomi Atom Cloud and a local runtime. So integrations that only connect to publicly accessible endpoints can be deployed to the Atom Cloud, and integrations that need to connect to local endpoints can be deployed to a local Atom. So what would cause you to consider the setup? Perhaps you have concerns about data overage fees from the Boomi Atom Cloud. Maybe you deploy large ETL integrations to a local runtime. Perhaps you have the need for high availability for real-time integrations, but you do not want to manage a molecule. So you can deploy real-time integrations to the Boomi Atom Cloud and run scheduled processes on a local Atom. Or perhaps you want the ability to configure and customize your runtime for specific processes. You can run those processes on a local runtime, and all other general processes execute on the Boomi Atom Cloud. There are some considerations to think about with a true hybrid approach. One is license counts. Remember that licenses are calculated by connection times runtime environments. So if you have one and the same connection that is deployed to local and to the Boomi Atom Cloud, that one connection will take 2 licenses. Similarly, if both runtimes, your local and your Boomi Atom Cloud, are attached to the same environment, perhaps your production environment, then every connection will consume 2 licenses because licensing is determined by the runtime environment that the process is deployed to. In this case, your runtime environment is both the local Atom and the Boomi Atom Cloud. It's not calculated simply by the runtime that is executing the process. So the recommendation here is to create 2 different production environments, one for each runtime, and then deploy the process to the specific runtime that will execute that process. One final consideration is that there is no direct interaction between the Boomi Atom Cloud and your local runtime. Another specialized hybrid is a cloud gateway. We have said that local endpoints require a local Atom, but what if you want those local endpoints to interact with outside customers? Well, you can create a cloud gateway that your customer can hit, which will then send a request to a local Atom running a web service. This makes your local endpoint available for processing without opening it beyond your secured network. This is useful when integrating a local endpoint with multiple trading partners. Boomi Atom Cloud forwards to the local runtime via web services, and the only question then is who will do the work. You can have a thick cloud and a thin local Atom where the Boomi Atom Cloud handles most of the processing and only calls to the process to access the local endpoints. Or you can have the reverse of that, where you can have a thin cloud, which is essentially just routing traffic to a process deployed with the local Atom to access endpoints that are behind the firewall. So this illustration shows the cloud gateway. All inbound traffic from external sources is sent to the public Atom cloud and then forwarded to local runtime via web services over a single trusted connection. Outbound traffic may also be sent from the local runtime to the Atom cloud for routing to external endpoints. Here are a few considerations for a cloud gateway. It simplifies your firewall configuration, intrusion, and certificates when you integrate with trading partners because that's handled in the cloud and not on your local network. Because there will be multiple processes and calls, it will be harder to track documents across multiple executions and ensure delivery and retry. All inbound traffic routes to the Boomi Atom Cloud, so be mindful of data volume usage. Alternatively, you can use a third-party external gateway technology. So you want to decide where the main processing will be performed. A lightweight setup would pass through the cloud with the heavy lifting on the local atom, or you can have the heavy lifting on the cloud and the lightweight local atom as a data retriever. Let's briefly cover a few runtime selection recommendations. This is how you decide which runtime is right for you and your organization. You need to survey your endpoints. Any kind of local access will dictate some form of local runtime. Consider your volume and availability. This will drive a decision for a higher availability runtime option. You may need to deploy quickly. In that case, the Boomi Atom Cloud is a quick way to get started. You should always be considering licensing. Connections are licensed per endpoint per runtime environment. Finally, you want to consider your own ability to manage and support the setup. You want to have a good understanding of the complexities of local runtime environments and evaluate your own resources before making a selection. The selection of a local clustered environment, such as a molecule or private atom cloud, should be based on the following considerations. There should be some motivation and non-functional requirements moving you in that direction. There should also be an adequate infrastructure skill set for management and troubleshooting of this setup. You might also want to consider that the most appropriate selection for you might be a hybrid or a specialized workload approach. In general, the Atom is a default starting point and a great starting point unless high availability requirements dictate some redundancy that's afforded by the molecule. Also, this is good for one-off and/or large ETL or migration use cases. The molecule is excellent for scheduled and stateful integrations. The group of atoms is a great solution for large-scale stateless web service integrations. And finally, the Dell Boomi Atom Cloud is excellent for small to moderate integrations with only cloud accessible endpoints.